Hello, and welcome to Sleepy Universe. Whatever day you've had, you can let it go now. There is nothing you need to do, nothing you need to solve. Tonight, we'll take a gentle journey through the silent lives of stars. We'll explore 100 sleepy facts about distant suns, from their first glow in stellar cradles to their final rest in cosmic darkness. You don't need to remember any of them. Your only task is to listen and let your mind drift among these gentle, shining lights. So, find a comfortable position. Feel your body grow heavy, supported by your bed. Let the weight of the day melt away with each breath. Just listen and imagine we are floating, untethered, in the deep, quiet expanse of space, looking out at a sea of shimmering, slumbering stars. Now, let your awareness float up, beyond the atmosphere, beyond the moon, and into the peaceful darkness where these ancient suns burn in perfect silence. Let's begin. Stars begin their lives in vast, dark, and beautiful clouds in space called nebulae. Picture these not as simple clouds, but as soft, silent cradles, immense and patient, drifting between the stars. They are made of the finest dust and the most gentle gases, and for millions of years, an invisible force, gravity, slowly, softly, pulls little pieces of this cloud together. It is a quiet gathering, a gentle collapse, until a warm, dense core begins to glow with its own light in the heart of the darkness. This is the birth of a star, a process so slow and peaceful it makes the rise and fall of mountains seem rushed. The color of a star is a quiet whisper that tells us about its heat. When you look at the stars, notice their colors. The red stars are the coolest, glowing with a deep, warm light, like the last embers of a cosmic fire, patient and enduring. The yellow stars, like our own sun, are warmer, offering a friendly golden light. And the brilliant blue-white stars are the hottest of all, burning with a fierce, vibrant, and youthful energy. This beautiful spectrum of color is a silent language, a way for the stars to tell us about their nature without making a single sound, a peaceful code written in the light that travels across the vast emptiness to reach our eyes. The most common stars in the universe are small, dim, red dwarfs. When we glance at the night sky, we often see the brightest and most brilliant stars, but they are the rare giants. The true majority of stars are the small, humble red dwarfs. They are not flashy or loud. They glow with a deep red light, burning their fuel with a slow and steady patience that is almost impossible to comprehend. These quiet stars can shine for trillions of years, far longer than the universe has even existed. They are the silent, enduring keepers of cosmic time, glowing softly in the vast darkness, a reminder that true strength is often found in quiet persistence. The light from the nearest star is a traveler from the past. When the gentle light of a star lands in your eye, you're not seeing it as it is now, but as it was long ago. The light from our sun is only 8 minutes old, a quick messenger. But the light from the very next closest star, a small red dwarf, began its journey over 4 years ago. Every single star you see is sending you a message from a different moment in history. The bright star Sirius, its light is over 8 years old. The giant Rigel, its light started its journey centuries ago. This means the night sky above you is a beautiful, slow-moving collage of the past, a tapestry woven from countless different yesterdays, all shining down on you in a single, peaceful now. A star spends most of its long life in a state of perfect, peaceful balance. For the vast majority of its existence, a star is in a serene and stable phase. Inside, two immense forces are locked in a gentle, eternal embrace. The tremendous crush of gravity constantly tries to pull the star inward, to make it collapse. But deep in the star's core, the powerful process of fusion creates an energy that pushes outward with equal strength. These two forces balance each other perfectly for billions of years. This beautiful equilibrium creates a long, steady, and quiet period of shining. It is the star's calm and constant adulthood, a timeless era of luminous peace. Our sun is a gentle, middle-aged, and wonderfully average star. Our own sun is about 4.5 billion years old, which places it right in the comfortable middle of its life. It is not the biggest, the smallest, the hottest, or the coolest star. It is wonderfully ordinary. It has burned through about half of the hydrogen in its core, and it has enough fuel left to continue shining with the same reliable, steady glow for another 5 billion years. It is a constant, gentle presence, a faithful star that provides just the right amount of light and warmth, creating a stable and peaceful home for our world to flourish. Its quiet reliability is the very reason we are here to enjoy this peaceful night. The weight a star has when it is born decides its entire life story, from beginning to end. A star's destiny is written from the moment it first begins to glow. A small, lightweight star will have a long, calm, and uneventful life, glowing softly for trillions of years. A medium-weight star, like our sun, will live a stable life for billions of years before ending its days in a gentle and beautiful transformation. But a very heavy, massive star will live a short, brilliant, and dramatic life, ending in a tremendous explosion that scatters new elements across the galaxy. There are no surprises. Its birth weight is its fate, a cosmic path set from the very start, allowing it to live its life in peaceful acceptance of its own nature. Stars themselves do not twinkle. The twinkling is a gentle gift from our own atmosphere. The beautiful, familiar twinkling of the stars is not something the stars do themselves. High above us, the air of our planet is never completely still. There are always gentle ripples and waves of warm and cool air drifting through the sky. As the steady, untwinkling light from a distant star passes through these ripples, the light bends and shimmers. This bending is what makes the star appear to twinkle and dance for us on the ground. It is a soft, atmospheric veil that adds a layer of gentle magic to the night. But in the true, silent emptiness of space, far above our atmosphere, the stars shine with a constant, steady, and untwinkling glow, like perfect, motionless diamonds. It is very common for stars to be born in pairs, dancing together through space. Many of the points of light we see are not solitary stars, but two stars born together from the same cosmic cloud. These are called binary systems, and they spend their entire lives in a slow, graceful dance around each other. Some pairs are so close they whirl around in just days, almost touching. Others are so far apart that their slow, stately orbit takes many thousands of years. It is a peaceful, endless ballet set to the silent music of gravity, a constant companionship in the vast, dark cosmos. They are never alone, always connected to their partner by an invisible thread of force, waltzing through the galaxy together. A star creates its light and heat by the gentle squeezing of atoms together in its core. Deep, deep inside a star, the conditions are unlike anything we can imagine. The pressure is immense and the heat is incredible. Here, in this quiet, hidden forge, the tiny atoms of hydrogen are pushed together so softly yet so firmly that they fuse and become a new type of atom, helium. In this magical process, a tiny, tiny bit of the atom's mass is transformed into a vast amount of pure energy. This energy is the star's light and heat. This process, called nuclear fusion, is the hidden heart of every star, the secret, peaceful fire that has kept the stars shining steadily since the very beginning of the universe. It is the ultimate recycling of energy, a gentle, powerful glow, born from the simplest of elements. The surface of the sun is a bubbling ocean of incredibly hot, bright gas. The part of the sun we can see is called the photosphere, which means sphere of light. It is not a solid surface you could stand on, but a churning, brilliant layer of intensely hot gas. From here, it looks like a smooth, bright disk, but if we could look closely, we would see it is actually a storm of peaceful activity. Great cells of hot gas, each as large as a continent, slowly rise to the surface, release their light, and then sink back down in a slow, constant, and graceful dance. It is a roiling, luminous ocean, forever moving and changing, all glowing with a brilliant, steady light that gives life to our world. Sunspots are simply cooler, temporary spots that appear on the face of the sun. Sometimes dark blemishes appear on the bright surface of the sun. These are sunspots. They are not truly dark. They are just slightly cooler than the intensely bright areas around them. They are created by the sun's powerful, tangled magnetic field. This magnetic field can act like a barrier, preventing some of the heat from rising up from the sun's interior to the surface. This makes that particular spot a little cooler and therefore a little darker than its surroundings. These spots come and go in a gentle, predictable cycle that lasts about 11 years, like the sun's own slow, magnetic heartbeat. The Pleiades star cluster is a family of young, bright stars that travel together through space, also known as the Seven Sisters. This is a tiny, misty, and beautiful group of stars you can often see on a clear night. They are not related to the other stars around them. They are a true family. These are young, hot, and blue stars, all born from the same cloud of gas and dust not long ago, in cosmic terms. They are still moving through space together, a beautiful, sparkling cluster of siblings, staying close to one another on their long, shared journey across the galaxy. Looking at them is like looking at a distant, glowing family, holding hands as they wander through the immense darkness. A star's true brightness, or luminosity, is the total light it gives off. This is different from how bright a star appears from Earth. How bright it looks depends on how far away it is. A star that is close might look bright, but actually be quite dim. A star that is far away might look faint, but actually be incredibly powerful. Luminosity is the measure of the star's real power, the total amount of light and energy it radiates into space every single second. It is the star's true voice, its authentic song of energy, telling us not how it appears from our small world, but what it truly is in the grand scale of the cosmos. Stars are the factories that create the elements that make up our world and our bodies. At the beginning of its life, a star fuses hydrogen into helium, but as it grows older, it begins to create heavier elements. In its core, it can start to fuse helium into carbon and oxygen. In the very largest stars, this process continues, creating neon, magnesium, silicon, and all the way up to iron. When these stars end their lives in great explosions, they scatter these newly forged elements across space. This stardust eventually becomes part of new stars, new planets, and eventually us. Every atom of carbon in your cells, every atom of oxygen you breathe, was once made inside a star that lived and died long ago. We are all, literally, made of stardust. Some stars, known as variable stars, rhythmically grow brighter and dimmer over time. Not all stars shine with a constant light. Some stars, like the famous mirror, actually pulse. They slowly grow larger and brighter, then smaller and dimmer, in a peaceful, regular rhythm that can take months. Others change their brightness because they have a companion star that periodically passes in front of them, like a slow cosmic blink. Yet others have giant, dark spots that rotate in and out of view. These gentle, predictable changes provide a slow, rhythmic heartbeat in the cosmos, a reliable and soothing metronome against which the quiet universe can measure its own long, patient age. The sun's outer atmosphere, its corona, is mysteriously much hotter than its surface. This is one of the most beautiful puzzles of our sun. The visible surface of the sun is very hot, about 5,500 degrees Celsius. But if you move outward into the sun's faint, wispy outer atmosphere, the corona that we see during a total solar eclipse, the temperature soars to over 1,000,000 degrees. How this outer, tenuous layer becomes so much hotter than the surface below is a question scientists are still working to answer. It is a quiet, enduring mystery of our closest star, a secret it keeps hidden until the moon perfectly covers its bright face, revealing the beautiful, hot, pearly white corona that crowns it. A light year is the almost unimaginable distance that light travels in one full year. It is important to remember that a light year is a measure of distance, not time. It tells us how far something is. Light is the fastest thing in the known universe, moving at an incredible speed. In just one single second, light can travel around the Earth 7 times. Now, imagine that speed sustained for an entire year. The distance it covers in that time, nearly 10 trillion kilometers, is 1 light year. This immense unit of measurement helps us understand the profound, quiet emptiness that lies between the stars. the vast dark spaces that separate the islands of light in our galaxy. The star we call the North Star has not always been and will not always be our guide to the north. The Earth wobbles very slowly on its axis, like a giant spinning top that is beginning to slow down. This slow, graceful wobble, which takes 26,000 years to complete, is called precession. It means that the star that appears directly above the Earth's North Pole changes over thousands of years. Right now, we are fortunate to have a fairly bright star, Polaris, as our North Star. But long ago, in the time of the ancient Egyptians, the star Thuban was the pole star, and in the far future, the bright star Vega will take its turn. The entire sky is in a slow, majestic motion, a grand, cosmic clock with a hand that moves once every 26,000 years. The star Betelgeuse is a massive, aging red supergiant, nearing the spectacular end of its life. That bright, reddish star in the shoulder of the constellation Orion is not like our Sun. It is a red supergiant named Betelgeuse, and it is truly enormous. If you were to place it at the center of our solar system, its puffy outer layers would extend all the way out past the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars. It is very old and unstable, pulsating in size and brightness. Astronomers know it is nearing the end of its life and will one day, perhaps in the next 100,000 years, end in a colossal supernova explosion. For a few weeks, it will shine brighter than the full moon, visible even in the daytime. It is a sleeping giant, resting in its final years, holding within it the seed of its own magnificent and final transformation. A star does not truly burn. It glows from the profound nuclear fusion in its core. Imagine the very heart of a star, a place of such immense pressure and such incredible heat that it defies all human understanding. Here, in this silent, hidden forge, the simplest of atoms, hydrogen, are pressed together so gently and yet so firmly that they merge. They become something new, helium. In this act of cosmic alchemy, a tiny, almost non-existent speck of mass is transformed into a burst of pure energy. This is not a fire like we know. It is a slow, steady, and magnificent transformation of matter into light. It is a process that has continued moment by moment for billions of years, a silent, powerful engine that fuels the star's gentle glow across the eons. The material that makes up our bodies was once inside a star long before our sun was born. Consider the calcium in your bones, the iron in your blood, the oxygen you breathe. Every single atom of these elements, every single piece of you that is not hydrogen, was created in the heart of a star that lived and died long ago. That star, unlike our sun, was massive and short-lived. It spent its life fusing elements, and when it could fuse no more, it ended its life in a tremendous, silent explosion, a supernova that scattered these newly forged atoms across space like cosmic seeds. These seeds eventually gathered over billions of years into the cloud that would form our solar system, our Earth, and us. You are not just living in the universe is living in you. You are made of ancient stardust, a walking, breathing memory of a star that died so that you could one day exist. The sun is not a perfect, steady flame. It has a slow, rhythmic heartbeat of activity. The sun may look constant and unchanging from our distant viewpoint, but it has a life of its own, a quiet pulse. Over a period of about 11 years, the sun's activity rises and falls. During what is called solar maximum, its surface is more active, with more sunspots and more frequent, beautiful eruptions called solar flares. During solar minimum, it grows calmer, its face more serene. This cycle is driven by the slow tangling and untangling of the sun's powerful magnetic fields. It is a deep, slow breath, an inhalation and exhalation that lasts for more than a decade, a gentle rhythm in the life of our parent star. When a star like the sun dies, it does not vanish. It creates a beautiful, glowing shell called a planetary nebula. After a star like our sun has spent billions of years in peaceful stability, it begins to change. It swells into a red giant, and then, in a final, gentle act, it sheds its outer layers into space. These layers do not simply drift away. They are illuminated by the hot, exposed core of the star, which remains at the center. This core lights up the expanding cloud of gas, causing it to glow in magnificent, intricate patterns of light. For about 10,000 years, a mere blink in cosmic time, this planetary nebula shines, a luminous ghost of the star it once was. It is a star's final gift to the cosmos, a beautiful, transient piece of art painted on the canvas of space before it fades away into the darkness. Some stars end their lives not with a gentle sigh, but as incredibly dense objects called neutron stars. When a very massive star reaches the end of its life, its core collapses. It does not simply shrink, it is crushed. The immense gravity forces the protons and electrons together, merging into neutrons. The entire mass of a star, 1.5 times the mass of our sun, is squeezed into a sphere, no larger than a city. The density is so unimaginably great that a single teaspoon of this material would weigh billions of tons. These neutron stars are the ultimate condensed remains of a giant, silent, and incredibly dense, drifting through the galaxy as tombstones to a violent and powerful end. The very largest stars can collapse into black holes, where gravity is so strong that not even light can escape. At the end of the life of the most massive stars, the core collapse is so complete, so total, that it creates a phenomenon where gravity becomes absolute. This creates a black hole. The boundary around it, the event horizon, is a point of no return. Once anything, a spaceship, a planet, or even a particle of light, crosses this invisible threshold, it can never come back. It is lost forever from our observable universe. A black hole is not a hole in space, but a region of space where matter has been compressed to an infinite density, a place where the normal rules of physics cease to exist. It is the ultimate victory of gravity, a silent, dark mystery in the fabric of space-time. Stars are not scattered randomly. They are gathered into vast, spinning cities of stars called galaxies. Our sun is not a lonely traveler. It is one of perhaps 100 billion stars in our home, the Milky Way galaxy. A galaxy is a gravitationally bound family of stars, gas and dust, all orbiting a common center. Some galaxies are graceful spirals, with arms winding slowly through space. Others are fuzzy, round ellipticals, or irregular shapes with no defined form. Each galaxy is an island universe, a great stellar community where stars are born, live, and die together, separated from other galaxies by millions of light years of nearly empty space. Our own galaxy, the Milky Way, is a barred spiral, and we live in its quiet suburban outskirts. If you could see our galaxy from the outside, it would look like a great, spinning pinwheel of light. At its center is a bright bar-shaped structure made of stars, with spiral arms unwinding from its ends. Our solar system does not reside in one of the bright, busy major arms. Instead, we are located in a smaller, quieter spur of stars known as the Orion Spur, nestled between the larger Perseus and Sagittarius arms. We are about halfway out from the bustling galactic center, in a peaceful neighborhood where the stars are not too crowded, a location that may have been crucial for allowing life to develop on Earth in stability and peace. The Andromeda Galaxy is our closest major galactic neighbor, and it is on a slow, inevitable course to meet us. In the constellation of Andromeda, a faint smudge of light is visible to the naked eye on a dark night. This is the Andromeda Galaxy, a spiral galaxy even larger than our own Milky Way. It is hurtling towards us through space at a speed of about 110 kilometers per second. But do not imagine a rapid collision. The universe operates on a different timescale. In about 4 to 5 billion years, our two galaxies will begin to slowly merge, their stars gracefully intertwining in a dance that will last for billions more years. The stars are so far apart that it is very unlikely any two will collide. Instead, the two galaxies will pass through each other and eventually settle into a new, larger galaxy, perhaps an elliptical one, a peaceful union of two great stellar families. The smallest stars, red dwarfs, are so efficient that they can shine for trillions of years, while giant stars blaze brightly and die young. The small, cool, red dwarfs are the ultimate marathon runners of the cosmos. They burn their hydrogen fuel so slowly, so carefully, that their expected lifetimes are longer than the current age of the universe. The first red dwarfs that ever formed are still shining today, barely changed from their youth, and they will continue to glow for trillions of years into the future. When all other star types have burned out and died, these faint red embers will still be there, quietly providing pockets of warmth and light in an increasingly dark and cold cosmos. The brightest star in our night sky, Sirius, is actually a binary star system. The brilliant diamond-like star Sirius, the dog star, is not one but two stars locked in a mutual orbit. The star we see easily, Sirius A, is a bright white main sequence star, but it has a tiny, incredibly dense companion, Sirius B, which is a white dwarf, the Earth-sized remnant of a star that has already died. Sirius B is so faint it requires a powerful telescope to see, but it orbits its brighter partner every 50 years. This brilliant beacon in our winter sky is a silent partnership between a star in its prime and the ghost of a star that was. A star's brightness, as seen from Earth, is called its apparent magnitude. This is a simple, ancient way of classifying the stars we see. The brightest stars were assigned the smallest numbers, with the very brightest having negative magnitudes. Sirius has an apparent magnitude of -1.46. The faintest stars visible to the naked eye have a magnitude of about +6. This scale is a logarithmic scale measure of how much light actually reaches our eyes, a way of mapping the sky not by the stars' true power, but by their gentle, perceived presence in our personal sky. The Hubble Space Telescope has taken deep field images, revealing thousands of galaxies in a patch of sky the size of a grain of sand. In one of the most profound experiments in astronomy, the Hubble Space Telescope was once pointed at a seemingly empty, dark patch of sky for days. The result was not darkness. The image was filled with thousands of tiny, faint smudges of light. Each one was not a star, but an entire galaxy, each containing billions of its own stars. This Hubble Deep Field image revealed that the universe is filled with galaxies as far as our telescopes can see. The empty spaces in the sky are an illusion. The cosmos is brimming with countless islands of stars, a testament to the overwhelming vastness and richness of creation. The dust and gas between the stars is known as the interstellar medium. The space between the stars is not a perfect vacuum. It is filled with an extremely thin mixture of gas, mostly hydrogen and helium, and tiny, fine grains of dust. This interstellar medium is the raw material for new stars. In some places, this material gathers into cold, dense clouds called molecular clouds, which are the birthplaces of stars. When a star dies, it returns some of its material, now enriched with heavier elements, back to this medium. It is the galactic ecosystem, a great cycle of cosmic recycling that has been ongoing for billions of years. The closest star to our solar system is the Proxima Centauri system. Just over 4 light years away, in the constellation of Centaurus, lies our Sun's nearest stellar neighbor. It is a small, faint red dwarf star called Proxima Centauri. It is part of a triple star system that includes the 2 brighter stars, Alpha Centauri A and B. Proxima Centauri is known to have at least one planet, Proxima Centauri b, which orbits within its habitable zone, the region where temperatures might be just right for liquid water to exist. This makes our closest stellar neighbor also one of the most intriguing in the search for life beyond Earth. The Sun is moving through space, carrying the entire solar system with it. Our Sun is not stationary. It is orbiting the center of the Milky Way galaxy at a speed of about 230 kilometers per second. It takes the Sun approximately 225 to 250 million years to complete one full orbit, a period sometimes called a cosmic year. The entire solar system, the planets, asteroids, and comets, is carried along with it, like a family riding a great cosmic carousel. We are all on this journey together, moving through the galaxy in a slow, grand, and majestic circle. The study of stars and their light is called spectroscopy, and and it allows us to know what stars are made of. When astronomers look at a star, they can break its light apart into a rainbow-like spectrum. Within this spectrum are dark lines, like a unique barcode. Each chemical element absorbs light at very specific colors. By reading these barcodes, scientists can determine the exact chemical composition of a star from trillions of miles away. They can tell what the star is made of, how hot it is, and even how fast it is moving toward or away from us. It is a form of cosmic chemistry, a way of listening to the silent song of a star and understanding its story. The constellation patterns we see are not real groupings. The stars are often at very different distances from us. The pictures we see in the night sky, Orion the Hunter, Ursa Major the Great Bear, are simply patterns drawn by human imagination. The stars that make up these constellations are typically not physically related to each other. One star in a constellation might be relatively close, only 50 light-years away, while another star in the same pattern could be thousands of light-years distant. They just happen to lie in the same general direction from our viewpoint on Earth. The constellations are a beautiful illusion, a two-dimensional painting on the celestial sphere, created by our own need to find patterns and stories in the heavens. The North Star, Polaris, is a Cepheid variable, a type of star that pulses rhythmically. Polaris, our current guide to the north, is not a constant star. It is a Cepheid variable, which means it gently pulses in size and brightness over a period of about 4 days. This type of star is incredibly important because there is a known relationship between its pulse period and its true brightness. This makes Cepheid variables one of the most important standard candles for measuring distances in the universe. Even the steadfast North Star has a gentle, rhythmic heartbeat, a slow breath that helps us map the scale of the cosmos. In the very distant future, the universe will become a much darker place as stars slowly die out. Stars are being born, but the rate of star birth is slowing down. The universe is using up its supply of gas, the raw material for new stars. Over trillions of years, the last stars will form, and then, one by one, they will all burn out. The large, bright stars will die first, then the medium-sized stars like our Sun, and finally, the long-lived red dwarfs will flicker out. The universe will grow progressively darker and colder, eventually leaving only the remnants of stars, white dwarfs, neutron stars, and black holes drifting. In an ever-expanding, silent, and dark cosmos. It is a future of profound peace and stillness, the final, quiet end of the stellar era. Imagine a star so dense that a spoonful of it would weigh more than a mountain. This is the reality of a neutron star, the collapsed core of a giant star. After a supernova explosion blows the star's outer layers into space, the core is left behind, crushed by its own gravity. The atoms that once made up the star are squeezed so tightly that electrons are pushed into protons, turning everything into a solid mass of neutrons. This creates a substance of unimaginable density, where the space inside atoms is eliminated. These silent, city-sized objects are the ultimate condensed matter in the universe. drifting through the galaxy as perfect dense spheres. Their surface gravity so strong that any bump or mountain would be no taller than a millimeter. Picture a star that spins hundreds of times every single second. Some neutron stars, born from the violent death of a massive star, are set spinning at incredible speeds. As the massive star collapsed, its core shrank, and just like a spinning ice skater pulling in their arms, it spun faster and faster. The result is a pulsar, a neutron star that spins so rapidly it completes multiple rotations in the blink of an eye. From its magnetic poles, it beams out radiation, and if one of these beams sweeps across the Earth, we see a regular pulse of light, like a cosmic lighthouse. This incredible spin is a silent, rapid heartbeat in the chest of a stellar corpse, a reminder of the violent forces that created it. Consider a star that is not made of atoms, but of a strange, soupy substance called quark-gluon plasma. Theorized by scientists, a quark star is what might exist if a neutron star is crushed even further. Under such immense pressure, the neutrons themselves would break down into their fundamental components, quarks and gluons. This would create a star made of a continuous, flowing soup of these elementary particles, a state of matter that hasn't existed freely since the first moments after the Big Bang. While not yet definitively discovered, the possibility of such an object hints at the strange and exotic forms matter can take under the most extreme conditions, a silent, enigmatic possibility in the cosmic zoo. There are stars that wander the dark between galaxies, alone and unattached. Not all stars belong to a galaxy. Through violent gravitational interactions, stars can be flung out of their galactic homes, sent drifting into the immense, cold voids between galaxies. These are called rogue stars or intergalactic stars. They travel through this profound emptiness, their light unchallenged by the glow of neighboring suns shining onto empty space. They are the ultimate loners, solitary travelers on a journey that will never end. Their planets, if they have any, forever locked in darkness, gazing up at a sky devoid of other stars. Envision two stars so close they share their atmospheres, dancing a delicate and intimate waltz. In a contact binary system, two stars orbit so closely that they actually touch. Their mutual gravity pulls material from their surfaces, forming a shared envelope of gas that surrounds them both. They are like two cosmic dancers, so entwined they have become a single glowing figure, spinning through space. This intimate embrace cannot last forever. Eventually, they may merge into a single, larger star, or undergo a more dramatic transformation. For now, they are a testament to the closeness that gravity can enforce, a binary star becoming one. Think of a star that is older than the galaxy it resides in. The universe's first stars, known as population 3 stars, are hypothetical giants thought to have formed from the pristine hydrogen and helium that existed after the Big Bang. They contained no heavy elements, lived fast, and died in massive explosions that seeded the universe with the first metals. While we haven't definitively found one, some of the oldest stars we have observed are nearly as old as the universe itself. These ancient suns, found in the halo of our galaxy are time capsules. Their light has been traveling for over 13 billion years, and their simple chemical composition tells the story of a time before planets, before many generations of stars, when the cosmos was new and fresh. Visualize a star that is not round, but shaped like a gigantic cosmic egg. Very fast spinning stars can bulge at their equators due to centrifugal force, becoming oblate spheroids, shaped like a beach ball someone is sitting on. The star Altair, one of the brightest in our sky, spins so rapidly that its equator is about 25% wider than its poles. It completes a full rotation in about 9 hours compared to our Sun's 25 days. This creates a star that is not a perfect sphere, but a gently squashed one, its shape a silent testimony to the powerful forces of rotation acting upon its fluid, gaseous body. Contemplate a star that is cold enough that you could touch its surface without being burned. At the very bottom of the stellar family are the brown dwarfs. These failed stars form like stars, but do not have enough mass to ignite sustained hydrogen fusion in their cores. Instead, they glow with a faint, deep red or infrared light from the residual heat of their formation. The coolest known brown dwarfs have surface temperatures comparable to a domestic oven, or even a warm summer day on Earth. They are not stars, nor are they planets, but something in between. Dark, warm orbs drifting alone in space, emitting a gentle heat that would be pleasant to the touch, a far cry from the inferno of a true star. Imagine a star that is fundamentally unstable, convulsing in massive eruptions that tear at its surface. Eta Carinae is one of the most massive and volatile stars known. It is a hypergiant containing over 100 times the mass of the Sun. It is so luminous and unstable that it experiences giant outbursts. In the 1840s, it had a great eruption where it ejected huge amounts of material, briefly becoming the second brightest star in the night sky. This material formed two vast, expanding lobes of gas that now surround the star, making it look like a cosmic peanut. Eta Carinae is a star living on the edge, a ticking time bomb that could explode as a supernova at any time in the next million years, a restless giant in its final turbulent years. Picture a star whose light is bent and magnified by the gravity of another star in front of it. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time. This means that light, traveling in a straight line through this warped space, appears to bend. When a foreground star passes directly in front of a more distant star, its gravity can act as a lens, focusing and magnifying the background star's light. This phenomenon is called gravitational microlensing. For a brief period, the distant star can appear hundreds of times brighter than normal. It is a natural cosmic magnifying glass, a silent and temporary alignment that allows us to see stars that would otherwise be far too faint to detect. Consider a star that pulses with a rhythm so precise it rivals atomic clocks. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like a lighthouse. The timing of these pulses is incredibly regular, some so stable that the slow, steady drift over millions of years can be predicted. This makes them superb natural clocks in the cosmos. Astronomers have used networks of pulsars to try to detect the faint ripples in space-time known as gravitational waves, using the cosmos itself as a laboratory. The steady metronomic tick of a pulsar is one of the most reliable rhythms in the universe. Envision the gentle breeze of particles constantly flowing from the sun, touching all the planets. The sun does not just give off light, it also emits a continuous stream of charged particles called the solar wind. This wind flows outward in all directions, a thin, hot plasma that travels at supersonic speeds. It carves out a vast bubble in the interstellar medium called the heliosphere, which envelops our entire solar system. When these particles are channeled by Earth's magnetic field toward the poles, they collide with our atmosphere, creating the beautiful, shimmering curtains of light known as the aurora. The solar wind is the sun's gentle, continuous exhalation, a whisper of its presence that reaches the very edges of its domain. Think of a star that is not a single point of light, but a vast, diffuse sphere of glowing gas. After a medium-mass star like our Sun ends its red giant phase, it gently expels its outer layers into space. The hot, exposed core of the star, now a white dwarf, illuminates this expanding shell of gas, causing it to glow. This is a planetary nebula. Despite the name, it has nothing to do with planets. Early astronomers thought their round shapes resembled planets. These nebulae come in astonishingly complex and beautiful shapes: butterflies, rings, and hourglasses, each a unique and fleeting masterpiece. They last for only about 10,000 years before the gas disperses, too brief a moment in cosmic time, a star's final, beautiful sigh. Visualize a star that is so large, its gravity pulls material from a companion star. In a close binary star system, if one star evolves into a giant, its outer layers can be pulled by gravity onto the surface of its smaller companion. More dramatically, if one star becomes a dense remnant like a white dwarf, neutron star, or black hole, it can pull gas from its living companion star. This gas doesn't just fall straight down, it spirals in, forming a hot, bright disk of material around the dense object called an accretion disk. This process can trigger brilliant X-ray flares, or, on a white dwarf, even cause a supernova explosion. It is a cosmic theft, a silent transfer of mass and energy between two closely bound partners. Contemplate a star whose final act is to create a glittering diamond the size of a planet. After a white dwarf star cools for billions of years, its carbon and oxygen interior can theoretically crystallize, forming a gigantic diamond-like structure. This hypothetical end state is called a black dwarf. The universe is not yet old enough for any white dwarf to have cooled to this point. The first white dwarfs are still glowing with residual heat at thousands of degrees. But in the far, far future, this will be the fate of stars like our Sun, to become cold, dark, Earth-sized crystals, drifting forever in the frozen, expanding darkness, a peaceful and permanent rest. Imagine a star that is not powered by nuclear fusion, but by the slow, relentless crush of gravity. Before a protostar becomes hot enough to ignite fusion, it already shines. This early light comes from gravitational energy. As the cloud of gas collapses to form the star, the material falls inward, picking up speed. When this falling material crashes onto the surface of the growing protostar, the energy of the impact is converted into heat and light. This is the star's first gentle glow, a warm light born not from nuclear fires, but from the simple, patient, and powerful act of collapse under its own weight, a quiet prelude to its brilliant future. Picture a star that is a churning, chaotic canvas of magnetic storms. The sun's surface is a dynamic place, dominated by its magnetic field. This field can become twisted and tangled, storing vast amounts of energy. When these magnetic field lines suddenly reconfigure and snap into a new arrangement, they release that energy in a spectacular eruption called a solar flare. In just minutes, a solar flare can release energy equivalent to millions of nuclear bombs, heating solar material to tens of millions of degrees and creating a burst of radiation across the electromagnetic spectrum. It is a sudden, violent storm on the face of our star, a testament to the powerful and dynamic forces contained within its seemingly calm exterior. Consider a star that is part of a vast, ancient swarm of hundreds of thousands of stars. Globular clusters are spherical collections of stars that orbit the centers of galaxies. They are densely packed, containing hundreds of thousands, sometimes millions, of stars gravitationally bound together in a perfect sphere. They are ancient, among the oldest objects in the universe, having formed when the galaxy was young. Their stars are metal poor, meaning they contain very few elements heavier than hydrogen and helium, indicating they were born before many supernovae had enriched the cosmos. These clusters are like celestial retirement homes, preserving a pristine population of old stars in a graceful, slow-moving dance. Envision a star that is slowly being consumed, its life cut short by a voracious companion. In some binary systems, a white dwarf, neutron star, or black hole can slowly devour its companion star. The intense gravity of the dense object pulls a stream of gas from the outer layers of its partner. This stream spirals inward, forming a bright, hot accretion disk before ultimately falling onto the surface of the dense object. For a white dwarf, this can eventually trigger a nova or even a Type 1a supernova. For the donor star, it is a slow death by dismemberment, its substance steadily transferred to its dead companion, a long, drawn-out cosmic drama. Think of a star that is not where it seems to be, its image warped into a perfect circle of light. When a massive object, like a galaxy or a black hole, lies directly between us and a distant star, its gravity can bend the starlight around it. In a perfect alignment, this bending can warp the star's single point of light into a complete circle, known as an Einstein ring. It is a beautiful and dramatic demonstration of gravity's effect on light, a natural illusion created by the curvature of space-time. These rare and perfect rings are like cosmic halos, allowing us to see the same star multiple times and in a distorted form, a silent echo of light on its long journey to us. Imagine a star that has used up its fuel and now glows only with the leftover heat of its former life. This is a white dwarf, the Earth-sized core of a star like our Sun, left behind after it shed its outer layers. With no nuclear fusion to support it, it is prevented from collapsing further only by a quantum mechanical force, the resistance of electrons being squeezed too close together. It does not create new energy. It simply radiates the immense heat stored within it, a fading ember from its fiery past. Over billions of years, this ember will cool, slowly changing from white to yellow to red, and finally to a cold black crystal, a peaceful and permanent rest in the cold of space. Picture a star so vast that its outer layers are not firmly bound, but form a puffy, tenuous envelope. Red supergiant stars, like Betelgeuse, are in the final stages of their lives. They have expanded to such an enormous size that their gravity holds their outer layers only very loosely. The surface of these stars is not a sharp boundary like the Sun's, but a gradual transition into a hazy, extended atmosphere. Material can easily drift away from these stars in a slow, constant stellar wind. They are like great, breathing celestial beings, their substance slowly exhaling into the surrounding space, preparing for their final transformation. Consider a star whose gentle wind carves and shapes the cosmos around it. All stars, including our Sun, lose a tiny fraction of their mass through a steady stream of particles called a stellar wind. For a calm star like the Sun, this wind is a gentle breeze. But for massive, hot stars, the wind is a powerful, relentless gale, flowing outward at millions of miles per hour. This wind carves vast cavities in nearby interstellar clouds, compresses gas to trigger new star formation, and sculpts the nebulae around the star into beautiful and complex shapes. It is a slow, persistent force of creation and destruction, a silent breath that shapes the galactic environment. Envision our solar system moving through a vast, empty bubble in space, carved by ancient stars. We reside in a region of space called the local bubble. It is a cavity in the interstellar medium, about 1,000 light-years across, filled with hot, thin gas. This bubble was not formed by our Sun, but by a series of supernova explosions from massive stars that died millions of years ago. Their powerful blasts swept up the surrounding gas and dust, clearing out this local space. Our solar system simply happened to be passing through this region, sailing on a calm sea created by the violent deaths of long-vanished stellar giants. Think of a star that is not a single color, but a blend, because it is actually two stars orbiting too close for our eyes to separate. Some of the points of light we see as single stars are, through a telescope, revealed to be two or more stars. But some binary stars are so close together in the sky that even telescopes see them as one. However, their dual nature can be revealed by their light. The combined light of the two stars, one perhaps blue hot and the other orange cool, blends to create a unique, composite color that hints at the secret partnership within. It is a silent collaboration of light, a single hue born from two distinct sources. Visualize a star that is a cosmic magnet of unimaginable power, a magnetar is a type of neutron star with a magnetic field 1,000 times stronger than an ordinary neutron star and a quadrillion times stronger than Earth's. This field is so powerful, it could erase the data on every credit card on Earth from halfway to the moon. The stresses in this field can cause starquakes on the magnetar's solid crust, cracking it and releasing immense flashes of gamma rays. These objects are the universe's ultimate magnets. Their invisible fields a dominant and violent force in their immediate space. Contemplate a star whose life is a delicate balance against its own immense weight. A star is a constant battle between two forces. The crushing force of gravity, generated by the star's own immense mass, tries to compress it into a tiny point. Pushing outward is the tremendous pressure from the nuclear fusion furnace in its core. For millions or billions of years, these two forces are in perfect, stable balance. The star does not expand or contract, it simply shines. This balance, known as hydrostatic equilibrium, is the defining state of a star's long, stable life. A silent, enduring truce between collapse and explosion. Imagine a star that pulses in and out, breathing like a great cosmic lung. Cepheid variable stars are a class of stars that rhythmically change size and brightness. They expand, growing larger and brighter, and then contract, growing smaller and dimmer over a period of days or weeks. This pulsation is a stable and repeating cycle, driven by a delicate interplay between the star's opacity and the storage and release of energy in its outer layers. This gentle, regular breathing provides a reliable cosmic heartbeat, a slow, luminous rhythm in the galaxy. Picture a star whose light is so faint and red that it is invisible to our eyes, but warm to the touch. At the bottom of the stellar mass scale, bordering on planets, are the coldest brown dwarfs. These objects are not massive enough to sustain hydrogen fusion, and after a brief period of deuterium burning, they simply cool down. The oldest and coldest brown dwarfs have surface temperatures similar to that of a warm room on Earth. They emit no visible light, only a faint glow in the infrared part of the spectrum. They are dark, warm wanderers, almost invisible, their presence betrayed only by the faint heat they radiate from their formation long ago. Consider a star that is the surviving member of a binary system, its partner vanished in a supernova. When a massive star in a binary system goes supernova, the explosion can violently disrupt the partnership. Sometimes the companion star survives, but is flung away at high speed, a runaway star. This star then travels through space alone, carrying with it the memory of its dramatic past, its motion, its composition, even its shock at the loss of its partner, are all silent witnesses to a catastrophic event that happened long ago. It is a stellar widow, forever carrying the story of its partner's violent end. Envision the quiet, patient drift of stars within a galaxy, like birds in a flock. The stars in a galaxy are not static. They are in constant, graceful motion, each following its own orbit around the galactic center. This is not a rigid, mechanical rotation, but a flowing, dynamic dance. Stars drift past one another, their gravitational influences gently tugging at their neighbors over eons. The galaxy is a living, flowing river of stars, not a frozen snapshot. This slow, graceful ballet has been ongoing for billions of years and will continue for billions more, a stately and silent procession. Think of a star whose light is not constant, but flickers because of great dark spots on its surface. Just like our sun has sunspots, other stars have star spots. On some stars, particularly active, cool dwarfs, these spots can be enormous, covering a significant fraction of the star's surface. As the star rotates, these vast, dark regions rotate in and out of view, causing the star's total brightness to dip and rise in a regular pattern. Observing this flickering light allows us to map the surface of these distant suns, revealing the presence of giant dark storms larger than our entire solar system. Visualize a star that is so new, it is still surrounded by the swirling disk of its birth. Young stellar objects, or protostars, are stars still in the process of formation. They are often enshrouded in the dense gas and dust of their parent cloud. At the center, the newborn star shines, while around it spins a flattened, spinning disk of leftover material, a protoplanetary disk. It is within this disk that dust grains collide and stick together, eventually forming planets, asteroids, and comets. This scene is a solar system in its earliest infancy, a star with its future family already taking shape around it. Contemplate a star whose final moments are so bright they can be seen across the universe. A supernova is the catastrophic explosion of a star. For a few weeks, a single star can outshine its entire host galaxy of billions of stars. The light from this one event can be visible from billions of light years away. It is a star's final, magnificent shout, a brilliant flash that announces its death across cosmic distances. In that fleeting, immense brightness, it forges and scatters the heavy elements that will one day form new stars, planets, and life, a final, generous gift to the cosmos. Imagine a star that is not a source of light, but a source of rhythmic, pulsing radio waves. A pulsar is a neutron star that emits beams of radio waves from its magnetic poles. As it spins, these beams sweep across space. If one of these beams crosses Earth, our radio telescopes detect a very regular, repeating pulse. These pulses can be incredibly precise, arriving with the regularity of a cosmic metronome. The first astronomers to discover them half-jokingly labeled the signal LGM for little green men, as the perfect regularity seemed artificial. We now know they are the natural lighthouses of the galaxy, their radio whispers telling us of the rapid spin of a stellar corpse. Picture a star that is part of a vast, flowing stream of stars, the remnant of a devoured galaxy. Our Milky Way galaxy grows by consuming smaller dwarf galaxies. When this happens, the stars of the dwarf galaxy are not instantly absorbed. They are stretched out by our galaxy's gravity into long, flowing rivers of stars that orbit the galactic center. These stellar streams wrap around the galaxy like great celestial ribbons, their stars moving together in a coherent flow. They are the ghostly remains of a galaxy that once was, a silent testimony to the slow, galactic cannibalism that has built the Milky Way over billions of years. Consider a star whose atmosphere is being stripped away by the intense radiation of a brilliant neighbor. In a binary system containing a hot, massive star and a cooler companion, the intense ultraviolet light from the hot star can heat the atmosphere of the cooler star, causing it to boil away into space. A stream of gas is pulled from the cooler star, flowing towards the hotter one. This is called Roche lobe overflow. The donor star is slowly being evaporated by its partner's fierce light, its substance slowly transferred, a gradual and one-sided sharing that will ultimately change both stars forever. Envision the quiet, dark space between the stars, where new stars are waiting to be born. The interstellar medium is the thin soup of gas and dust that fills the galaxy. In most places, it is incredibly tenuous, far better than any vacuum we can create on Earth. But in some regions, it gathers into cold, dark clouds called molecular clouds. These clouds are the nurseries of stars. Within their dark, dusty folds, shielded from outside light and radiation, pockets of gas can collapse under their own weight. This quiet, dark, and cold emptiness is the necessary precursor to the brilliant light of a new star, the deep silence before the cosmic dawn. Think of a star that is a cosmic chameleon, changing its appearance over its long life. A star does not look the same from birth to death. A star like our Sun was born as a contracting protostar, shrouded in dust. It then spent billions of years as a stable, yellow, main sequence star. In its old age, it will swell into a red giant, glowing with a cool red light. Finally, it will shrug off its outer layers to reveal a hot blue-white white dwarf, which will then cool and fade. A single star can be many different kinds of objects throughout its lifetime, a slow and beautiful transformation over billions of years. Visualize a star that is a reliable lighthouse for cosmic navigation, its distance known with absolute certainty. For astronomers to measure the vast distances of the universe, they need landmarks with known brightness called standard candles. Certain types of stars, like Cepheid variables and Type Ia supernovae, have properties that allow us to know their true intrinsic brightness. By comparing this known brightness to how faint they appear from Earth, we can calculate their distance with great precision. These stars are the mile markers of the cosmos, their reliable light allowing us to map the scale and expansion of the entire universe, guiding us through the immense depths of space. Picture the gentle, eternal pull between a star and its planets, an invisible bond that holds worlds in their orbits. Gravity is the silent, patient force that orchestrates the dance of solar systems. A star's gravity creates a well in the fabric of space-time, and planets travel along curved paths within this well. This is not a forceful tug, but a gentle, continuous guidance. It is this unseen hand that keeps Earth in its stable, yearly journey around the Sun, allowing for the consistent seasons and the conditions that make life possible. It is a constant, quiet embrace that never falters, never tires. Consider a star whose light is a coded message, telling us the story of its birth and life. When astronomers study the spectrum of a star, the rainbow of its light broken apart, they can read dark and bright lines like a cosmic barcode. These lines reveal the star's chemical composition, its temperature, its density, and even how fast it is moving towards or away from us. A star rich in iron and carbon tells a story of being formed from the remnants of earlier supernovae. A simple, hydrogen-rich star speaks of a more ancient birth. Every star's light is its autobiography, written in a language of physics, waiting for us to gently read its story. Envision a star that is not alone, but at the center of a bustling family of planets, moons, and asteroids. Our Sun is the heart of a complex planetary system, but it is not unique. Thousands of other stars have been found to have their own families of exoplanets. Some have giant gaseous worlds orbiting perilously close to their star. Others have rocky planets nestled in the habitable zone, where temperatures might be just right for liquid water. Each star with planets is the center of its own unique cosmic story, a potential sun for other worlds, with its own rhythms, its own histories, and its own possibilities. Think of the solar wind, a gentle, endless stream of particles flowing from the sun, shaping the environment of every planet. The sun constantly exhales a thin, million-mile-per-hour breeze of charged particles. This solar wind flows outward in all directions, filling the solar system and defining the space between the planets. It interacts with planetary magnetic fields, causing beautiful auroras. It slowly erodes the atmospheres of worlds without a protective magnetic shield. It is the sun's way of gently touching all its children, a constant, subtle influence that reminds every planet, comet, and asteroid of the central star that binds them all together. Visualize a star in its final, majestic act of becoming a red giant, gently engulfing the worlds that once orbited it. As a star like our Sun nears the end of its life, it swells into a red giant. Its outer layers expand hundreds of times beyond their original size. In this process, the inner planets, Mercury, Venus, and likely Earth, will be swallowed whole. They will not crash into a solid surface, but will spiral gently into the star's vast, tenuous outer atmosphere, vaporizing as they descend. It is a slow, peaceful, and inevitable absorption, a star reclaiming the worlds it gave birth to, bringing them back into its fiery embrace. Contemplate the quiet, empty spaces between stellar systems, where the light of one star yields to the light of another. The space between stars is so vast that it is mostly a profound emptiness. A spaceship traveling from the sun to the nearest star would spend over 4 years in a void where the sun is just a particularly bright star and the destination is a distant point of light. In this interstellar space, the light from one star slowly fades and the light from another gradually strengthens. It is a place of transition, of quiet solitude, where the influence of one sun ends and the domain of another begins. Imagine a star that is a cosmic variable, its brightness changing in a slow, predictable rhythm over years or decades. Not all variable stars pulse quickly. Some, like mirror-type variables, change their brightness over periods of many months. These are old, cool, giant stars that breathe in a slow, deep rhythm. They swell and shrink, growing brighter and fainter in a cycle that is as regular as it is leisurely. Watching such a star is an exercise in cosmic patience, observing a heartbeat that takes a full Earth year or more between pulses. It is a slow, luminous meditation. Picture the galactic year, the 250 million year journey our Sun takes around the center of the Milky Way. Our solar system is not static. It is on a grand, slow-motion carousel ride around the galactic center. One complete orbit, a cosmic year, takes approximately 225 to 250 million years. The last time our solar system was in this same position in the galaxy, the dinosaurs were just beginning their reign on Earth. In this great, silent journey, the Sun carries all its planets, comets, and asteroids along with it, an entire family on a slow, majestic voyage through the galaxy. Consider a star that is a delicate balance of forces, where a change in its internal pressure would mean its end. A star's existence is a fragile thing. The outward pressure from fusion in its core must exactly balance the inward pull of gravity. If fusion were to suddenly stop, gravity would crush the star in a matter of seconds. If fusion surged unexpectedly, the star would blow itself apart. This perfect dynamic balance is maintained for millions or billions of years. It is a sustained, quiet miracle of physics, a constant, precise equation that results in the steady, reassuring glow of a star. Envision the ghostly glow of a nebula, the illuminated remains of a star that died long ago, now a cradle for new stars. When a massive star dies in a supernova, or a sun-like star gently sheds its layers, it creates a cloud of gas and dust. If this cloud is near a hot, bright star, it will glow, reflecting the starlight or fluorescing under its intense radiation. These nebulae are often the most beautiful objects in the sky. Veils of red hydrogen, blue reflected starlight, and complex dark lanes of dust. They are both tombs and nurseries, the recycled material of dead stars now being incorporated into the next generation of suns and planets. Think of a star's magnetic field as an invisible architecture that shapes its atmosphere and activity. A star's magnetic field is a complex, invisible structure generated by the churning, electrically conductive plasma in its interior. This field channels the star's outer atmosphere, guiding solar flares and shaping prominences that loop hundreds of thousands of miles into space. It creates the star spots that dot its surface. It is the hidden skeleton of the star's outer layers, a powerful, shifting framework that governs much of the star's visible personality and activity, all without ever being seen directly. Visualize a star that is a member of a moving group, a family of stars born together and traveling in the same direction. Stars are often born not alone, but in clusters from a single giant molecular cloud. While many clusters eventually disperse, some stars remain as a moving group, a set of stars, not necessarily close together now, but all moving through the galaxy on parallel paths their motions tracing back to a common origin point. They are like siblings who have left their childhood home but still walk in the same direction, a scattered family still connected by their shared history and shared velocity through the galaxy. Contemplate the concept that every star is a sun, and every sun is a possible day for another world. From our perspective, other stars are tiny points of light, but from the perspective of a planet orbiting one of those stars, it is their sun. It is their source of day and night, of heat and light and energy. It is the center of their universe. Every single star we see is or could be the bright center of a solar system, with its own family of planets, its own rhythms of dawn and dusk, and its own potential for life and beauty that we can only imagine. Imagine the quiet, patient process of a star forming, a slow collapse over millions of years. The birth of a star is not a sudden event. It is a slow, gradual process of collapse under gravity. A dense knot within a cloud begins to fall in on itself. It takes hundreds of thousands of years for a protostar to form, and millions more for it to heat up enough to ignite fusion and become a true star. There is no explosion, no sudden flash, just a slow, patient gathering, a gentle warming, and then the first soft glow of sustained nuclear fire, a new light kindled in the dark. Picture the Lagrangian points, the places of gravitational balance in a star's system where objects can rest peacefully. In the space around a star, there are special points where the gravitational pull of the star and its planets create zones of stability. These are called Lagrangian points. Here, the competing tugs of gravity balance out, and an object, like a small asteroid or a spacecraft, can orbit the Sun while maintaining a fixed position relative to a planet. They are peaceful harbors in the gravitational sea, quiet parking spots in space where an object can rest, held in a perfect and silent balance between competing forces. Consider that the star you are looking at tonight might no longer exist. Because light takes time to travel, the stars we see are from the past. For the most distant stars visible to the naked eye, their light may have been traveling for thousands of years. For some of the faint, distant stars in telescopes, their light has been traveling for millions of years. It is entirely possible that some of the stars we see in the sky have already died in supernova explosions. The light from their death has simply not reached us yet. We are watching a live performance of the universe, but on a delay of centuries, millennia, or eons. Envision the Milky Way, a soft, hazy band of light in the sky, which is the combined glow of countless distant stars. The Milky Way is not a cloud, but a perspective. When we look at that soft, luminous band arching across the night sky, we are looking edge-on into the disk of our own galaxy. The hazy light is the unresolved combined glow of hundreds of billions of distant stars so far away that their individual lights blur into a continuous, gentle radiance. It is the collective light of our galactic city, a silent, sprawling metropolis of stars, of which our sun is just one humble citizen. Think of a star's life as a beautiful, slow-burning candle, whose wax is its own substance. A star is a candle that burns its own wax. The wax is the hydrogen fuel in its core. The flame is the nuclear fusion process. Gravity provides the constant pressure that keeps the wick burning steadily. For billions of years, the candle burns, slowly consuming itself, transforming its mass into light and heat. And when the wax is nearly gone, the flame changes, flickers, and then either goes out gently or flares up in one final, brilliant flash. It is a beautiful, self-consuming sacrifice that provides light for the cosmos. And finally, know that the gentle, constant presence of the stars is a reminder of the deep, enduring peace of the cosmos. However chaotic our days may seem, the stars are a testament to a larger, quieter reality. They follow their ancient paths with unerring patience. They burn with a steady, silent light. They are born, they live, and they die on timescales that make our human worries seem fleeting. To look at the stars is to be reminded of a fundamental peace that underlies all of existence, a peace that is vast, dark, and beautifully illuminated by countless gentle suns. Let their quiet, constant presence assure you that rest is natural, that silence is profound, and that you are a part of this magnificent, sleepy universe. Good night.